Designing massive organic frameworks, like OLED displays or biological enzymes, requires us to model the behavior of thousands of atoms simultaneously. Exact quantum mechanics provides a physically rigorous way to do this, but trying to apply those exact equations to a molecule of that massive scale hits a brutal computational wall. Every quantum calculation forces a choice. You can have perfect mathematical accuracy, or you can have a result before the end of the decade. This chart shows the relationship between computational cost and correlation accuracy. Up here in the top right, high-level methods like coupled cluster offer incredible precision, but their computational cost scales exponentially with the size of the molecule. For massive organic frameworks, they are simply impossible to run. To study large systems, chemists rely on a different family of tools. Down here in the lower left is the operational zone for semi-empirical methods. They sacrifice a degree of absolute accuracy to achieve the speed necessary to process enormous molecules. The core premise here is practical. Rather than demanding flawless mathematical purity from the Schrödinger equation, semi-empirical models actively strip away the most difficult parts of the calculation. This graphic diagrams the semi-empirical philosophy. You take rigorous quantum mechanics and subtract the complex interactions clogging the computer. This subtraction happens in two ways: isolating only the chemically active electrons and physically amputating the heavy electron-repulsion integrons. Computational chemistry at scale requires a strategic trade-off, choosing exactly which parts of physical reality to ignore to make the math workable. Take domain isolation, for example. In conjugated organic molecules, the physical behavior of the electrons is cleanly separated. This model maps out that separation. At the base, the sigma bonds form a rigid structural skeleton. Hovering above are the mobile pi-electrons. They delocalize across multiple atoms, dictating the molecule's electronic properties, like color and conductivity. Because the physical behavior is separated, the math can be too. A method called Hückel theory simply deletes the rigid background framework from the calculation, focusing exclusively on these active pi orbitals. Removing that background leaves two primary variables: the baseline energy of an electron on one carbon atom and the bonding strength between neighboring atoms. This model reveals how delocalization works. As pi electrons spread over more atoms, the entire system gains extra structural stabilization. This diagram shows a conjugated pi system behaving like a particle in a quantum box. In a short molecular chain, there is a large energy gap between the highest and lowest molecular orbitals. Extend the conjugation length, and it acts like lengthening that quantum wire. The electrons spread out, compressing the energy levels together. This shrinking gap means the light absorbed shifts from invisible ultraviolet down into visible red light. Predicting macro properties like color doesn't require computing every single electron. Simulating only the active ones provides the necessary accuracy for real-world design. Yet, even after isolating just the active electrons, scaling your calculation up to thousands of atoms triggers a secondary, far more brutal mathematical bottleneck. The exact equations require calculating how every electron repels every other electron. This graphic represents the two-electron four-center integral, tracing complex interactions between multiple disparate orbital points in space. Computing the differential overlap for every possible combination creates a massive proliferation of equations. As the basis set grows, the total number of required integrals scales exponentially, overwhelming even the most powerful supercomputers. To process anything larger than a few atoms, chemists have to selectively amputate a massive portion of this math. This is solved through a truncation strategy known as the Neglect of Differential Overlap, or NDO. The physical intuition behind NDO is straightforward. If two orbitals are located on completely different atoms and their overlap is incredibly weak, their interaction is mathematically negligible. This breaks down the approximation. In reality, two separate atomic orbitals combine into a complex, difficult-to-calculate overlap density function. But if those orbitals belong to different atoms, the software simply erases it, declaring that specific overlap product to be exactly zero. The computational consequence is staggering. By setting these distant interactions to zero, millions of complicated electron-repulsion integrals instantly vanish from the workload. Of course, there is an obvious flaw here. By deliberately ignoring actual physical interactions, the accuracy of the quantum model degrades significantly. This is where we return to the final piece of the overarching semi-empirical philosophy: experimental parameters. To fix the math they just broke, chemists adjust the remaining variables so the outputs fit known, real-world experimental data. Measurements like heats of formation and observed molecular geometries act as a synthetic patch for the deleted integrals. NDO methods succeed precisely because they are not mathematically flawless. They intentionally break the Schrödinger equation, relying on reality itself to course-correct the math. Those original, severe amputations were a product of the early computing era. As hardware improved, chemists didn't abandon NDO. They carefully refined the severity of the approximation. This evolutionary tree charts that progression. The earliest methods used complete neglect, a fast but crude simplification, stripping away almost everything. Today, software relies on the NDDO standard. It neglects overlap only under strict conditions, retaining crucial terms and using sophisticated experimental parameterization. Because these modern models are so heavily fitted to specific data, they do possess a critical vulnerability. Face them with unusual bonding structures or complex transition metals that fall outside their training data, and the models will fail. But when applied to large, chemically conventional systems, their inherent weakness is overshadowed by their ultimate strength: unprecedented computational speed. This speed enables the high-throughput material screening required to discover new OLED displays. It allows researchers to map out the approximate reaction paths of massive biological enzymes and run molecular dynamic simulations over timescales that would otherwise be impossible. By isolating domains down to the essential actors and truncating the integral math through NDO, decades of continuous computation are collapsed down into manageable hours. Semi-empirical chemistry prioritizes pragmatism, trading first principles rigor for the speed required to navigate the complex molecular frameworks of organic